Yeah, dear students, welcome back to the visualization lecture on uncertainty visualization. That is the third and last part, and I want to start it with a short recap on uncertainty visualization techniques that were presented in the second part. We see here an example which I would say is quite classical. Uncertainty about values is determined as a scalar value, and that scalar value is mapped to a color scale from a certain color for low uncertainty, or one could say these data are certain, to those that are highly uncertain, and the color scale is chosen such that our attention is guided particularly by the high uncertainty regions. Here the same data is visualized in another way, namely the surface is perturbed in an extent that corresponds to the amount of uncertainty. That means when we see sharp surfaces, then indeed we have reliable data. But when the surface looks uncertain, yeah, because there is a lot of noise around it, then it is indeed uncertain. And I would agree with the authors of this paper that this is the more intuitive method. Here we see data that is uncertain with respect to a border. Yeah, so that's a kind of positional uncertainty. Here we see in black the most likely contour, but we also see a margin around it, a tube. Yeah, and this margin has not the same size everywhere. It is thicker here, for example, where the uncertainty is higher. And here is also a region with higher uncertainty, whereas other regions are more certain. Here we see an alternative visualization of the same data, namely some blurring is introduced here. So the contrast is lower in regions around this contour where the uncertainty is higher. Yeah. And the final example, again, two uncertainty visualization techniques shown side by side so that you can compare them. And again, they are applied to the same data. Yeah. We have a weather forecast here that relates to the temperature that is expected in the next hours. Yeah. So you see the cycle of the day here. So every 24 hours we have high values and low values and high values again, but not exactly the same high values. That's the variation in the weather. And different simulation models were used. And here you see what is called spaghetti plot, that basically all these predictions are shown simultaneously. That indeed gives a clue about the uncertainty. Yeah. If in a particular time they would be all very close to each other, that's more reliable. But it's hard to figure out what actually happens here. Yeah. Here instead, the same data is used to compute a probability density distribution, and from this certain values are derived, e.g. the maximum that is predicted or the minimum that is predicted. That is the median of the predictions, that's like this here, and this is the 25 percentile and the 75 percentile. Yeah, so some key values of this distribution are shown instead of all values that tend to produce visual clutter. Yeah, that as a recap. These were static visualizations. Yeah, I want to make you aware that like we discussed for many other visualization topics, also with respect to uncertainty, interaction is crucial. Yeah, that means users should be able to adjust how uncertainty is presented. There may be different preferences, starting with things like colors that are preferred, but maybe even more important, the amount of information that should be displayed should be adjustable. Yeah, so it should be possible to disable uncertainty visualization at all. Yeah, and also of course then to enable it again. Yeah, there should be interactions that allow to adjust what I call the visual dominance of the uncertainty component of the visualization. Is primarily data shown, and uncertainty is an add-on that is shown at selected regions where it is particularly high, and even there it does not dominate, or is uncertainty shown in such a way that it may in 3D, for example, occlude the actual data visualization, and in other situations lead to a situation that the attention falls more to the uncertainty aspect. Both can make sense in different situations. There should be interaction techniques. Yeah. And then we discussed that there are different ways of showing uncertainty, static visualizations. We have also seen examples of animations where continuous movement is created through the different variants. We have intrinsic methods like color coding or explicit ones where additional glyphs also are shown. I would not argue that all of them should be implemented and available, but not just one of them. Yeah, users should have a choice between a few variants. By the way, I recently heard a talk about decision making, and indeed, for people, it's typically a good situation if they can make decisions on the one hand, and on the other hand, maybe not too surprising, the number of decisions that they can make should not be too high. Yeah, 7 is often mentioned as a threshold here. If there are more decisions, then people, yeah, if this is exceeded, people get confused, and that's not ideal. Yeah, and then of course we also need evaluation. Yeah, and I've briefly mentioned this already in the last video lecture. I want to elaborate a little bit more on this. On the one hand, we want to assess how effective a certain uncertainty visualization technique is. By the way, which gets a bit more difficult with interaction, yeah, because then there are many variants of how the visualization technique can be used. But I would argue that also the visualization along with the interaction should be assessed. Yeah, and evaluation can be carried out at different levels. The first would be to identify the presence of uncertainty in specific regions. Are users able to recognize here are regions with high uncertainty? The second level is to assess the amount of uncertainty. Yeah, we want to see whether users are really able to compare this. So, and then I see that I made a mistake here. There is a third level, and that is decision making. Yeah, at the end, it is important which decisions users make based on the visualized uncertainty. Yeah, in many papers, I only read evaluations that relate to these two levels. But sometimes and increasingly, I see that also decision making is taken into account, and I would argue that this is really important. The major motivation to visualize uncertainty is to improve the decisions that are made on the basis of the visualizations. So, and then of course, it is still useful to measure task completion times. That's the probably most frequently used evaluation method at all. Yeah, how long do users take with something? However, one must be a bit careful to interpret this. Yeah, I would say with respect to uncertainty visualization, the goal is not that users are as fast as possible, because this is typically achieved with no uncertainty visualization at all. But of course, you want to understand how much the task completion time is extended in order to appropriately take into account uncertainty. Yeah, and I would also ask for user satisfaction. I mentioned in the first video lecture on uncertainty that uncertainty visualization aims to trigger system 2 thinking, which is not comfortable, which is slow and conscious. So it would not be surprising if user satisfaction is not very high with uncertainty visualizations. People tend to prefer easier visualizations, yeah. But nevertheless, it is important to understand how strong is this effect of maybe a reduced user satisfaction, because at the end, of course, visualization techniques incorporated in a product that have no user acceptance cannot work as well. Yeah, so therefore user satisfaction is also important, but like with the task completion times, I want to make you aware of the fact that an honest report of user satisfaction probably does not lead to very good results. So it needs to be interpreted with care. Yeah, let me describe a few use cases. One of them, quite popular one, when is my bus? Yeah, so the scenario here is that we want to make use of a real-time prediction of the departure of the next bus. Yeah, imagine I'm in my apartment. I know the bus stop is 8 minutes foot walk away. I'm looking at my smartphone and it tells me the next bus is in 10 minutes. So I should hurry up and go to the bus stop. Of course, this prediction is not 100% reliable. Yeah, that depends on the freshness of the prediction. Yeah, when it was updated for the last time. It depends on the current traffic situation. Yeah, like with all forecasts, the more time in the future that is forecasted, the lower is the certainty of this. Yeah, so therefore, it could be useful to quantify this uncertainty, to estimate it based on some of the aspects that I just mentioned, and to make this estimation also available to the user. Yeah, so here are just a little bit more thoughts on how to actually quantify the uncertainty. That's the basis, of course, for any uncertainty visualization. So, and K et al. Found out that typically these estimation times follow a normal distribution. So here you see the Gaussian curve. So instead of presenting a value like 8 minutes, for example, one could imagine a diagram that starts here maybe with 4 minutes and 6 minutes, 8, 10 and 12. And it tells you that in some cases the bus is even earlier than you thought, but it may be also later to a certain extent. Yeah. They compared different techniques and basically argued that this continuous representation is probably not ideal, so they transformed it into a discrete representation, yeah, where you have dots. For this purpose, they compute the cumulative density function. That is, if you add all the values for every point that are on the left side, then this gives you this curve. And these lines here indicate, basically the distance between the lines indicates the steepness of the curve. So here the curve is not very steep, so therefore the distances are larger here as well. And here is a region where it is particularly high, and therefore the lines have only a very low distance. These distances are used to compute the positions of these dots. And of course, an obvious parameter of such a visualization is the number of dots. If you would increase it to a very high amount, then more or less it is a transition towards a continuous representation, so that does not make sense. Yeah, but an essential question is, of course, how many points you should use. 20, 50, 100, maybe these are all reasonable numbers. In this example here, 50 dots are used, and if I think of a particular time, yeah, like I have 8 minutes, the prediction is 10 minutes, then there may be a small risk that the bus is even arriving earlier. Yeah, that's the small risk that I miss the bus. Yeah, based on the current estimation. So, and therefore that is shown in another color that's a bit more attention grabbing. And then you may think about, well, how important is it whether I get the bus or whether I miss it? Should I be absolutely on the safe side? Then there should be no red dots and I should start walking 3 minutes earlier. That will certainly depend on when the next bus after this one will arrive, and also on what kind of meeting or whatever I have and how important it is to be there absolutely in time. So with this in mind, it makes sense also to think of the next bus. So here it's predicted that the next bus comes in 10 minutes and the bus after this one in 38 minutes. Yeah, and that is conveyed here in different variants with density plots. I would say that's a conventional visualization, with these dot plots where the distribution is discretized in 20 points or 100 points. And here in a stripe plot where instead of dots, stripes are shown and the density conveys the likelihood that a particular timing applies. So you see that 10 is not only the middle here of this distribution, but that all values around 10 are much more likely than values that are further away in the past or in the future. Yeah. So you may imagine that was used for the evaluations. Users should compare such visualizations. Yeah. And what was the result of the evaluation? Most users prefer indeed visualizations that convey uncertainty. Not all of them. Yeah, there are users that say, well, that's all confusing to me. Give me the best possible estimate that you can make, and then I'm fine with this. Yeah. There was an interesting correlation saying that users that prefer uncertainty visualization and used one of the techniques shown before have more trust in the visualization, and with this also in the underlying system. Yeah. And what became really clear in the interviews that were part of this evaluation is a situation where an arrival time is estimated without any uncertainty Q, even if a few users prefer this. But when it then turns out that the estimated arrival time is just not true, yeah, it is really, it deviates strongly from this, then trust in this whole system is really ruined. That may easily happen if for example, sensors do not work, and instead of a sensor-based real-time prediction when the bus arrives, it just shows the time based on the schedule. Yeah, and then there may be an obstacle and the bus cannot come at all or comes an hour later, and all the time it tells you when the next bus will come according to the schedule, and the large amount of uncertainty that is involved is just not conveyed at all. A second example, which I chose because I think that's really an important one for broad audiences, for many people, that's called range anxiety. And it relates to the fear of running out of power, which may happen with every car, but of course the lower ranges currently are associated with electric vehicles, and users of electric vehicles typically are novice users of these vehicles, so they have not so much experience of what can happen and how to interpret this. Yeah, so therefore that's a severe problem. Not only that the ranges are lower, but also that you cannot rely so much on the estimated further driving time that you have with this amount of battery charge. So that's the scenario. Yeah, the estimated range depends currently in the cars only on the battery state. It does not involve the outside temperature, for example, or the driving style, or the weight of persons in the car and the baggage. And if it would be combined with a navigation system, then it could become obvious that there are mountains in front of you. And yeah, if you have to go over these mountains, that of course has an influence on the range that you can further drive. Yeah. So on the one hand, we need better uncertainty estimations, but we also need to convey the resulting uncertainty that still exists. Yeah. Without any uncertainty depicted, what happens often is that the estimated range drops down suddenly, yeah, and that's perceived as frightening. Yeah, how can it be displayed? A few examples here. Gradient plots, one technique that we have seen in an earlier lecture, yeah, where the highest likelihood is that we can, in this example, drive about 30 miles and here 85 miles, but depending on some aspects that are not under full control of the system, it could be that already after 75 or even a bit earlier, we don't have enough battery, but with good luck, it could be that we even achieve 95 or 100 miles. Yeah, that is what I would call a certainty visualization. Yeah, it includes no uncertainty clue at all, and that is the variant that is transformed to an uncertainty visualization. Of course, that requires a careful quantification of the uncertainty. Yeah. And again, I want to make a few comments on the evaluation, which I think is really inspiring and very good, because it was carried out in the real situation. Yeah, so they managed to integrate variants of the visualization directly in the display of the car. So they had to cooperate, of course, with the car company to do so. And not only that people sit here in a lab and do something, but they really drove on highways in the countryside and in suburban regions. Here you see an elevation profile. So you see that there are approximately 400, almost 500 meters that had to be climbed. Yeah. So the users had to drive 20 miles with a mixture of different traffic situations and a challenging height profile. And the researchers wanted to understand how the way that the further range is communicated influences the driving style, and also how this is influenced, of course, from the battery state, and also how this affects the stress level and trust. Yeah. It turned out that in particular novice drivers of electric vehicles benefit from uncertainty visualization, for example, with these gradient plots. When the system estimates a higher range, that indeed has an influence on the driving style. Yeah? People drive a little less careful in the sense that they are a bit more agile. In case of a lower range estimation, that was the scenario with the 30 miles, they really do a lot in order to drive more economically. Yeah, and also the stress level is lower, is higher in the low range estimation. That's an error. It is higher. Yeah, so having vehicles with larger capacity and having more charging points and having more accurate predictions, all this is necessary, yeah, and will certainly be done in the future. But range anxiety alone cannot be avoided with this. Yeah, uncertainty visualization is also important, but uncertainty visualization without improvements in these areas will also not be sufficient to fight range anxiety. Yeah, so I think that's the quite interesting use case. Yeah, here's an older example. You see that the visualization looks not so nice, has not the best resolution and so on. It's almost 20 years old and relates to hurricane prediction. That means currently the hurricane is here over the ocean. And the question is where it enters the land and how it will proceed in the future. Yeah, so that's the predicted trajectory. Yeah, here we have a kind of directional uncertainty or trajectory uncertainty, and that leads, of course, also to differences in the points in the regions that are actually affected. Yeah, as usual, the uncertainty increases over time. So that is here for Tuesday, for Wednesday, for Thursday. Any prediction for Sunday, that's 5 days in the future, of course, involves high uncertainty. Yeah, but people in these areas should be aware it may turn out that they have to leave their homes. Yeah, then let me give another example related to vector visualizations. In vector visualization, often analytical methods are used to represent the flow. Examples are streamlines and path lines and streak lines. For static flow fields, streamlines are used. Yeah, so that is based on a numerical integration. Yeah, you cannot analytically solve these integrals. You do this numerically, and you may remember from math lectures, numerical integration involves different things. For example, a certain step size that influences the accuracy of the results, but also different methods that take more or less points in the surrounding into account. So here for numerical integration, primarily Runge-Kutta methods and Euler methods are used. Yeah, and it would be interesting to show streamlines along with the uncertainty that is just based on the numerical integration. There may be further uncertainty based on the underlying raw data and the processes to collect them. So here we just think about the further uncertainty introduced in the numerical integration process. Yeah, stream ribbons or displacement glyphs, for example, can be used to represent the uncertainty. Here's an example. A streamline is shown with ribbons, and the thickness of the ribbons represents the local uncertainty, yeah, which is low in these regions here that are shown with very thin lines, and then you have thicker lines or even some regions that are really thick. The tube here is quite thick. That means here the uncertainty is higher, yeah, just based on the numerical integration. Here is another visualization that compares the two variants, Runge-Kutta numerical integration and an Euler integration. And both variants are shown here. I think the integration starts here and then goes all the way up, and the differences between the two become larger over time. Yeah, and that is nicely visualized here with this glyph-like visualization. Yeah, let me also show examples from geospatial data. I mention often that in cartography, many visualization techniques have been first used, have been introduced and pioneered. Here is an example where soil thickness is, on the one hand measured, and the measurements are used as input in a model. And models, as you know, contain simplifications and assumptions, so they have a certain uncertainty. And in cartography, this is just one example, uncertainty is frequently mapped to whiteness. Yeah? If you compare these two visualizations here, you see that a color scale for the soil thickness is used, and that's exactly the same here and here for regions with a higher certainty, where the uncertainty, that is the x dimension here in this diagram, is in the region of 40 to 50%, which already is quite a lot. But here it's even much higher. And if the uncertainty is really high, then they map just everything to white, which basically means you see no more differences there. In regions where the uncertainty is really high, and therefore the display of the measured values would be confusing, you just don't recognize any differences, and that avoids misleading conclusions. Yeah, and you see that this is a continuous transition, so the contrast is reduced more and more if the uncertainty gets higher. Yeah, that's, I think, a quite useful technique. One may think about the specific thresholds that are used here. Yeah, so there should be interaction to adapt this a little bit, but in principle, I think that's really a quite good way to visualize uncertainty. Yeah, of course, that's an example of continuous uncertainty instead of having just a few different certainty values. Yeah, briefly, I want to mention also astronomy, and there we have coordinates related to the stars, determined by parallax, and they are uncertain, and yeah, since these stars are in very different distances from us, this uncertainty also has very different scales. Yeah, so there is positional uncertainty and trajectory uncertainty about where these stars will move in the future. And in this paper here, by the way, you see that's the same paper that we have seen here already from Lee and colleagues. So they discussed a number of uncertainty visualizations that uses ellipsoids. Ellipsoids have the nice property that they can be scaled independently in the X, Y, and Z direction. So they can show the different uncertainty in these three directions. Yeah. And the trajectory uncertainty with respect to the future position is mapped to tube-like structures. So that's about astronomy. Back to a medical example. In the first video lecture, we discussed animation, yeah, a dynamic method, with respect to a transfer function, that is a kind of volume rendering, and the transfer function parameters were changed over time slightly in order to support the diagnosis of vascular structures with respect to a potential pathology, and in particular with respect to the question, is there a narrowing, a stenosis within the vessels? Similarly, for this purpose, also surface visualizations can be used. So instead of the little fuzzy look of a volume rendering with semi-transparent components, here we just have a binary decision. Does a certain point in the data belong to a surface? Yes or no? And that depends on a threshold value. And it may be very sensitive towards this threshold value, which you see here. The threshold value is only slightly changed between these two images, which you can easily verify because most of these images are the same. But in this example, you would say this person is completely healthy, whereas here it looks not only like a narrowing, but really like an occlusion. This person must have an infarct. And from the clinical symptoms, you would see, well, he has no infarct. So therefore, here it would also be useful to create an animation that changes the threshold slightly. And to make users aware of the fact that they never should rely on just one visualization with one threshold, but that they have to slightly adapt it. In particular, if they suspect there is really something wrong. Another medical example relates to diffusion tensor imaging for neurosurgery. Diffusion tensor imaging is a kind of magnetic resonance imaging. A couple of measurements are carried out there, at least 6. 6 measurements, that corresponds to the 6 components of a symmetric tensor. And what is measured here is the amount of diffusion in different direction. If we have a situation where diffusion is possible in all dimensions in the same extent, then we would say we have isotropic diffusion. That would be the case, for example, if you are in the middle of water. When diffusion is strongly anisotropic, that means it goes in one direction, but not in the orthogonal directions. It is likely restricted by something, for example, by the myelin sheath of the fiber tracts in the brain. So you can visualize this taking into account anisotropy measures, and at the end you need an anisotropy threshold. And like with the previous example with the vessel visualization, it really depends on this threshold. Here is a fractional anisotropy. That's probably the most popular anisotropy measure, a value between 0 and 1. And here it's 0.3, which gives you more fiber tracts than here with 0.32. So that's a quite small increase, but that avoids, for example, that these red fibers here are shown. So again, you could apply the same strategy that we just discussed before. Instead of generating one visualization, generate a sequence of visualizations, maybe starting with fractional anisotropy of 0.25, ranging to 0.4, with a step size of 0.01. You make a small animation and show these 16 different possibilities. Here's another strategy that was used for uncertainty visualization. Namely, they computed based on the uncertainty margins around the fibers and showed this instead. Here, the blue band represents what is certainly part of a fiber tract, whereas the circles around it in yellow represent how extended this fiber tract could be. So that's for neurosurgery. That means the surgeons have to plan how to operate, for example, how to remove a tumor without damaging one of these fiber tracts. Because if they would do this, that would have very severe consequences for the patients, often more negative consequences than the disease that they actually wanted to treat. So, and just to comment a little bit, what does it mean to compute an anisotropy measure? If you have a tensor, that's a 3x3 matrix, you can compute the eigenvalues of this tensor. And since in this case it's a symmetric tensor, there would be 3 real eigenvalues, no complex numbers. And by convention, they are ordered such that lambda 1 is the largest of the 3 eigenvalues, lambda 2, and lambda 3 is the smallest. Anisotropic diffusion would mean that lambda 1 is much larger than lambda 2, and with this, it's also much larger than lambda 3 because lambda 2 is larger than lambda 3. Yeah. Isotropic diffusion would mean, of course, there is also one ISO value that is larger than the others, but the difference is very small. Yeah. So lambda 1 is almost the same size like lambda 2 and lambda 3. A final medical example relates to Kaplan-Meier plots. Kaplan-Meier plots estimate the survival time of patients for different treatments, for example, or for different stages of a disease. Yeah. So we start here, point 0, and everybody is alive. And after a year, for some variants, still everybody is alive, but for some, a few already died. Yeah, and if we look at this point here, after 2.5 years, the green curve represents a situation where half of the persons already died, and later, even for the better curves, the red one here, after 5 years, basically all of them are dead, and after 4.5 years or 4 years, half of them died. Yeah, so these are Kaplan-Meier plots, and this is the typical example, which I would again call a certainty visualization. Yeah, because it does not involve any uncertainty related to these 4 estimates over time. Yeah, and there is uncertainty involved, and the uncertainty, like with every prediction, is stronger and higher with more time. Yeah, and here there is another reason why this is the case. You started with a certain sample size, let's say 1,000 people. Yeah, and you make statistics basically related to these 1,000 people. But the more time goes by and the more people die, you have lower and lower sample sizes. So at some point, if only one person dies, that already has a strong influence on the estimated survival. Yeah. So therefore, that is a better variant here that indicates the actual measurements, namely whenever someone died. Yeah. And it gives this margin here that is considerably larger here after 5,000 days, that is approximately 15 years, compared to the situation in earlier times. Yeah. So another example of an uncertainty visualization. Of course, if you include uncertainty in this manner and use it not only to show one curve, but like in this example to compare 4 curves, that makes the visualization more complex, a bit cluttered, and with this, of course, also more difficult to interpret. Task completion times will be longer, and maybe even user satisfaction will be a bit lower than with a certainty visualization. But the certainty visualization may be a bit misleading. Let me summarize these 3 video lectures on uncertainty visualizations. We have seen many techniques to display various types of uncertainty. Most of them were related to value and positional uncertainty. Some of them also related to trajectory uncertainty, as we have seen with the fiber tracts or the hurricane direction. All of this, of course, requires that uncertainty is carefully quantified, and often that's the major bottleneck. Often there are a few sources of uncertainty in the data that can be algorithmically evaluated and assessed, but there are also other types of uncertainty that are very hard or even impossible to assess. Yeah, that of course would be a problem. I focused deliberately more on techniques that are quite general. Yeah. But we have seen also examples that are really adapted to certain domains like geographic visualizations or anatomy. The medical examples I have shown could also be applied to volume data in other areas. So for example, there's also industrial CT data, and if you apply volume rendering to industrial CT data in order to understand about the shape of some industrial product, then the same problems may occur as we have seen with vessel visualization. Yeah? So a high sensitivity towards parameters of the transfer function. So the medical examples could be at least partially generalized to other areas. Most experience in uncertainty visualization is related to geospatial applications. Yeah, I use this acronym GIS here for Geographic Information Systems. If you would search in Google Scholar or so for uncertainty visualization, you would see a lot of examples for this. We briefly discussed also interaction, interaction in order to enable or disable uncertainty visualization, to assess the visual dominance of uncertainty visualization, and with this to adapt uncertainty visualization to the preferences of a particular user. I commented on comparisons and usability studies that are definitely necessary. I have read a number of publications on uncertainty visualization where I had the impression they were academically interesting to explore the design space of how can we visualize the uncertainty, but they were not carefully adapted to workflows in practices, to decision-making processes. At the end, we really must do something also in this kind of visualization that fits the needs of the users. I have the impression that some examples that I discussed a bit more, like this range estimate problem for electric cars and this bus arrival problem, really served needs of real users, and I also appreciated the evaluations that were done in very realistic settings. But in this direction, more research is necessary. Let me briefly look at the references and comment a little bit on them. As usual, of course, I mentioned everything that I used to prepare this video lecture, but some of them I would say are more important if you are interested in this topic to go a little bit more in detail. This survey article here from Ken Broadley and colleagues, approximately 20 pages of 30 pages. That's quite useful, quite comprehensive. I learned a lot from this paper here from Corell and Mike Gleicher. Error bars considered harmful, because I was not so aware of this harmfulness of error bars so far. And of course, a paper in a leading visualization journal cannot only criticize something, they came up with alternate encodings that are quite useful. As a short introduction in uncertainty visualization, this paper from Chris Johnson is quite interesting, visualizing errors and uncertainty. And this book of Daniel Kahneman discusses many topics, by far not only uncertainty, but uncertainty is something that occurs frequently in the book. It is basically about human decision making and about why this decision making often is systematically biased and leads to wrong decisions, and that people underestimate the amount of uncertainty in data and models and predictions is one of the most frequent reasons for wrong decisions. That is what Daniel Kahneman really explained very well. Finally, I want to mention Christine Potter's paper on ensemble visualization. That is the situation when we have a couple of simulations for weather forecasts, climate models, and so on, and a discussion of how that can be visualized. With this, I want to thank you for your attention.